Good evening, everyone. My name is Prasunamba and I am from Educative World. I am currently doing an automotive embedded systems internship at MHC. As a part of this internship, I have completed a project titled EV ADAS Dashboard, Real-Time Electric Vehicle Telemetry and Driver Assistance System. So, in this project, we designed real-time electric vehicle monitoring system using the STM32 microcontroller. We simulated various vehicle parameters and ADAS features in PiximLab and transmitted the data to a Python-based dashboard using UART communication. The dashboard displays vehicle real-time status and provides driver assistance alerts for safety driving. So um, now I would like to explain the project in detail. So before discussing the project, let us first understand the problem. Modern electrical vehicles generate a large amount of real-time sensor data, such as the speed, battery, state of charge, simply SOC, and motor temperature, torque, and driving range. Monitoring all these parameters manually is difficult. So, in addition, ADAS features like collision detection and blind spot monitoring all are very important for providing improving driver safety. So without a centralized dashboard, it becomes difficult to monitor both the vehicle performance and the safety information simultaneously. So as a result, important warnings or fault may be dismissed. So to overcome this problem, we developed an EV ADAS dashboard system. Our system displays all important vehicle parameters on a live Python dashboard through UART communication. It also provides collision warnings and blind spot detection, motor temperature monitoring, fault alerts, and different drives modes such as eco, normal, and sport. So this enables real-time vehicle monitoring and improve driving safety. And so this slide shows the overall architecture of our EV ADAS dashboard system. So on the left side we have the sensor inputs. Mm, the acceleration pedal and the brake pedal provide analog inputs, while electronic sensor ultrasonic sensors are placed at the front, left and right sides of the vehicle to detect nearby obstacles. And the analog signals are converted into digital values using the ADC. This ADC of the STM32F103C8T6 microcontroller. Inside the microcontroller, the EV control code um, processes parameters such as the speed, torque, battery state of charge, range, and driver mode. And this is about the EV parameters. When it comes to ADAS, the system uses the data from the ultrasonic sensors. These sensor measures the distance between the vehicle and the objects present at the front, left, and the right sides. Based on this distance data, the system performs obstacle detection, collision detection, and the blind spot detection to improve driver safety. If any unsafe conditions is detected, the system generates fault alarms messages and activates the required alerts. Finally, all the processed EV and ADAS data is transmitted through the UART communication to the Python dashboard where it is displayed in real time for continuous vehicle monitoring. So the next is it was the 9 development phases that we followed to complete our EV ADAS dashboard project. So the first We set up the development environment by installing the required software tools such as STM32Cube IDE and PiximLab and Python. Next, we configure the GPIO, nothing but the general purpose input and outputs, and peripherals followed by interfacing the ADC to read analog sensor inputs such as accelerator and brake pedal. So after that, we developed the EV dynamics model to calculate parameters like speed, battery state of charge, and the torque and range and driving mode. So then we implemented the ADAS functionality using the ultrasonic sensors for obstacle detection, collision detection, and blind spot detection. And the next phase involved designing the fault and alarm system to generate safety alerts whenever abnormal conditions were detected. Finally, we established UART communication to transmit the real-time temporary data from the STM32 controller to Python dashboard. And the next is ultrasonic ADAS engine. So we have placed three ultrasonic sensors around the EV vehicles. Around the vehicle, the one at the front and one at the left and the right. So these sensors continuously measure the distance between the vehicle and the nearby objects. Based on this distance information, the ADAS system provides several safety features. The first feature is a forward collision warning and or FCW. If any obstacle is detected in front of the vehicle within the predefined state of distance, and the system generates a warning. If the distance becomes critically low, a critical alert is displayed. The second feature is the time to collision, time, or TDC. This estimates how much time is left before the vehicle may collide with an object based on the current speed and the measured distance. And the third feature is blind spot detection or BSD. The left and the right ultrasonic sensor monitor the vehicle blind spots. If another vehicle or object is detected in these areas, the driver receives a warning. So, finally, the fourth feature is parking assistance, which helps the driver park safely by continuously displaying the distance to nearby obstacles. And then this slide explains the fault detection and alarm priority system used in our project. The STM32 microcontroller continuously monitors different vehicle parameters such as temperature, SOC, collision status, ultrasonic sensor health, and UART communication. If any abnormal condition it is detected, a corresponding fault bit is set in the fault register. Based on the fault we get, the system classifies it into four alarm levels. Alarm none indicates normal operation with no faults. Advisory indicates a minor issue that requires attention, and warning represents a moderate fault that needs immediate action. Critical is the highest priority level and indicates a serious condition requiring urgent response. These alarms levels are transmitted to the Python dashboard through UART, where the driver can easily identify the fault and take the necessary actions. So um, now I will explain how the STM32 microcontroller communicates with the Python dashboard. We use UART communication, nothing but so with a baud rate of 115,200 bits per second for fast and reliable serial data transfer. The controller sends two telemetry frames. The first frame contains the EV parameters such as speed. You can see it here: speed, SOC, and torque, temperature, range, and acceleration, and brake, um, which are taken from the potentiometers. And the next one is ADAS frame that shows front distance, left distance, and right distance, and time to um, and blind spot detection, alarm, and fault. So the Python application continuously reads these UART frames, decodes the data, and updates the dashboard in real time. This enables smooth visualization of both EV performance and adapts safety information with very low communication delay. And the next is Python matplot library dashboard, yeah, which displays all the EV and ADAS information in real time. The dashboard reverse refreshes at 10 frames per second, providing smooth live monitoring. On the left, we have speedometer, which shows the current vehicle speed with the color indicates based on the speed range. Next, the battery panel displays the state of charge SOC along with the estimated driving range and the selected drive mode. The speed history graph continuously plots the vehicle speed over time, allowing us to analyze the speed variations. The EV metrics panel shows important parameters such as torque, acceleration percentage, brake percentage, and motor temperature, alarm status, fault code, and the UART communication status. Finally, the ADAS displays the distances from the front, left, and right ultrasonic sensors along with the collision warning, blind spot detection, and time to collision information, giving the driver a complete safety overview. Overall, this dashboard combines EV and the ADAS safety features into a single real-time monitoring system, making vehicle operation safer and easier to analyze. Um, Results and demo. We will see the demo after this. So this completes the presentation of the project. Now I would like to give you a live demonstration of EVRS dashboard to show how the system works in real time. So I am opening STM32 Cube IDE. It takes some time. Yeah, this is the code that we have to exactly write in STM32 microcontroller. Yeah, we can see here. The first of all, we include all the header files like string, studio, main, common.h, that EV control, ultrasonic.h, ADAS, fault, and regarding UART. So and then we initialize and we call back all of them, and we initialize all of the functions regarding that. And yeah, so this is a print status function that which is used to display all the parameters like speed, SOC, temperature, torque, acceleration, brake, and range. And we can see time to collision, front, left, and right. Yeah, we can see here. And the system clock configuration function. Yeah, this is our code. Um, when we build it, when we get zero errors, then it is ready to display. You can see it is building right now. Yeah, we got almost zero errors. So next, open Pixim Lab. So this is a Pixim Lab board that contains STM32. We can see here STM32F103CAT6 board and reset buttons, all of this. So here we have to load our binary file. Yeah, it's loading. Yeah, this is our spare parts. We can see these are the four potentiometers that we are using instead of sensors in real time. The potentiometers acts here for accessing acceleration pedal. It is acceleration pedal and brake pedal and SOC and temperature. These indicates these parameters, and it is a virtual IO virtual terminal, and these three are ultrasonic sensors which are represent the front and left and right distances, and these are four LEDs which are red, blue, green and yellow. That indicates Generally, green indicates normal operation, everything is safe. Blue indicates information or active status. It shows live sensor readings or active ADAS features, for example, ultrasonics or distances. Yeah, yellow represents a warning and advisory. The driver should be cautious. And red indicates a critical condition, immediate actions is required. So these now, yeah, you can see what is going on here. Mm, yeah. This is a virtual terminal that indicates, yeah, you can see speed is 19.9 and SOC 100, torque and temperature range, acceleration, brake, front, left and right, and TTC, collision, blind spot detection, alarm and fault. So yeah, it is showing that fault 5 is running, so it displaying yellow LED. So after this, um, let's display these parameters on the Python dashboard. So how we are going to display these? By using the Python code. The Python code, when we run this, we will get this dashboard. This is a Python dashboard that displaying speed. This is a speedometer. This is a Python dashboard we usually see when we experience a real-time electric vehicle. We can see that a board behind steering. So this is generally that Python dashboard. In real time, we can see HMI displays, but now in our project, it is nothing but a Python dashboard. So this is including speed, 21 kilometer per hour, and this is a speed history that is decreasing slowly, and this is a battery percentage that is nothing but SOC. It is 62.7 percentage, and this includes 2087 kilometers that have to left that it covers by using these 62.4 percentage of charge. So it is in a normal mode right now, and these are the EV metrics, EV parameters, like torque is 79 and 80. It is changing. Acceleration, brake, no brake at all now, and the motor temperature, alarm, fault, and signal. These are showing here. And then in the right side, we can see it is ADAS bird eye view. So this is our vehicle, and this is our front vehicle or object. This is our right vehicle, and one more thing is the left side should be have, but it is not displaying my own. And so this is displaying, um, you can see this is displaying the distance between our vehicle and the other objects. It is 95 centimeters and 20 centimeters, and it is showing that before we when we start, alarm is advisory. Now it is none. So this is our project about EV and ADAS dashboard. Yeah, thank you.